Hello, this is Trevor Wallace, and today I will be explaining the gas laws using Bakugan. Now, Bakugan are these little marble toys from the 2000s that have a sort of magnet effect to them, and when that magnet effect triggers, the ball opens up. Now, I will be using several properties of the game today to demonstrate how exactly these gas laws work. We shall be starting with none other than Boyle's Law. Now, before we commence forth with Boyle's Law, I would like to mention that since we're talking about gas laws while also using physical matter here, I figured I should include that some of these equations for the gas laws are going to be modified to accommodate for these physical objects in comparison to normal gases we'd be doing this on. Now, to begin with Boyle's Law, I would like to mention the equation, which is pressure times volume equals the second and new pressure times the volume. This is an inverse relationship, and just some extra facts about the Boyle's Law in general and Robert Boyle himself. So Robert Boyle was born in 1627 in Ireland. He became a physician, or a physicist, and that is how he came to study the information that led to the creation of Boyle's Law. So this was a group effort between Robert Boyle and Robert Hooke. They published their findings in 1662, which eventually became known as Boyle's Law. So they discovered this gas law by developing an air pump together to study pneumatics, which was prior to finding the gas law. They published their findings in new experiments, physico-mechanical, touching the spring of the air and its effects. Yes, and one more interesting fact, Boyle's Law can also be called Mariott's Law, as this relationship was also supported by French physicist Edmé Mariotte. So, to demonstrate Boyle's Law here, we can take this little Bakugan I have here, and we can show that as I increase pressure on this Bakugan, its volume will actually decrease because it decreases in length. So to represent this in an equation, I used the volume, I represented this as a rectangular prism instead of a normal sphere, just to make it simpler doing the equations. So I found the volume of it as in its extended form, which would be about 72 cubic centimeters. Now, usually in the lab, this is represented as a volume in milliliters. However, since this is not a liquid or easily, it cannot exactly fill a container that easily, we're just going to be representing this as cubic centimeters. Then in this closed state, it is 3 centimeters in both length, width, and height. So I found this to be 27 cubic centimeters. Now to find this, I represented it in its base open form as having the standard temperature pressure. So I put this at exactly 1 atm times 72 centimeters cubed. So 1 atmospheric pressure times 72 cubic centimeters, which equals 27 cubic centimeters times the pressure. So this calculates out to about 2.7 atmospheric pressure to actually close this and get it into its spherical form. Next, we shall be moving on to Charles' Law, so see you momentarily for that. Alright, now it is time to discuss Charles' law, which is the equation volume over temperature equals the new volume over the new temperature. This is a direct relationship between volume and temperature. Now for some intriguing factoids upon the Charles' law. So, Jacques Charles was born in 1746 in France. As an inventor, he also invented the hydrometer and the reflecting goniometer. He also helped Nicholas and Anne Jean Roberts develop one of the first hydrogen balloons in 1783. French physicist suggested the relationship in 1787 of Charles' law, and then this law was later backed by Joseph Louis Gay-Lussac with empirical data. Now to get to the actual law itself in demonstration here. So, to represent volume, we already know that this Bakugan has this one right here. This one has a volume of 72 cubic centimeters in its open state. Now, we do not know the volume of this Bakugan right here. We do, however, have this gate of fire right here, which we can determine just using some estimations. This is just a normal card, but for the sake of the demonstration, we're going to use this Pyrus energy marker right here of 150 and represent that in Fahrenheit. For the flowing waters, I took a temperature scan of this card just to figure out what temperature it is, and it is at a temperature of 69.7 degrees Fahrenheit. So, calculating this all out to Kelvin, found that the flowing waters card has a Kelvin temperature of 294.09 degrees Kelvin, while the Gate of Fire card has a temperature of 338.71 degrees Kelvin. With these Kelvin temperatures, I put 72 centimeters cubed over 338.71 degrees Kelvin, and I set that equal to 294.09 degrees Kelvin, which is dividing the volume. So, after calculating this out, I got that this Bakugan right here is about 62.5 cubic centimeters, which rounds up to about 63 cubic centimeters, which I did do some measurements on this Bakugan just to see if I could, just to get it a Bakugan that was as close to the number as possible, which this one, doing a certain method, is in fact 63 cubic centimeters. Now that, we shall be moving on to our final law for discussion, which will be none other than the law of Graham's law, yes. Alright, now it is time to explain Graham's law. So, Graham's law is basically the equation that, it's an inverse equation that states that as the molar mass of a gas increases, their speed will decrease. This is basically saying heavier gases are slower than lighter gases. Now, there are some interesting facts about Graham's law. One is that Thomas Graham was born in 1805 in Glasgow of the UK, and despite his father wanting him to become a minister in Scotland, he actually became a chemist. He invented the dialyzer to separate colloids from crystalloids. He then developed the field of physical chemistry with his book, Elements of Chemistry. Finally, he was bestowed the title Master of Mint, a title once held by Isaac Newton for coin production. Now, getting into the example here, what we have is just two Bakugan down here. You can't really see, but I chose one, which is the smallest type of Bakugan. It is a B1 Bakugan. This one's pretty small, smaller than the ones I've been showing so far. Now, this one is the biggest Bakugan. This is a Deca Bakugan, about the size it could fit right in my palm. Now, we're going to be rolling these two Bakugan at the same time to see if they can land on that card right over here. Well, yes, they'll land on the card here, and we'll see which one stands quicker, and we could just calculate it from there. There we go. I'd say that will suffice. It seemed like they stood at about the same time. But don't forget there's also the activation period, which, since this one is smaller, it can activate a bit. It'll be like fully out quicker. So, now to get to the actual mathematics of all this. Basically, to sum it up, we're just going to be applying practically random gases here to these two Bakugan. So this little one right here, this one will be applied cyanide, and the larger one will be applied NO2, which is nitrite. So, doing the equation, the square root of 46.01 over 26.02, the molar mass of nitrite on top and cyanide on the bottom, divide and square root that will be that nitrite is about 1.3 times faster than NO2. So, with that, that is 3 gas laws covered using Bakugan. So, yes, thank you for watching.